This is a tutorial for the Direct Shear Lab of the Geotechnical Engineering course Civ E3208. The purpose of this lab is to analyze the performance of a sample of coarse-grained soil in shear. To test this, we will be using this shear box apparatus. It consists of the following components: a shear box which rests on a series of bearings and so is free to move back and forth, a motor which drives the testing box forward at a steady rate, a jig to apply a specific load directly on top of the soil sample while in shear, a force gauge or load cell which will record the amount of shear being applied, and two strain gauges, one vertical which will record any consolidation that takes place, and one horizontal which will record the horizontal displacement. Obtain a sample of soil in a container and record the mass of the soil plus container. In our case, we will be using this sand. Assemble the two halves of the shear testing box by aligning the holes and tightening the 4 screws. Fill the testing box with soil like this. Fill the box most of the way, leaving a space of about ½ centimeter. Gently compact the soil using a hammer. Use this flattening tool to flatten the surface of the soil. The tool also shows what level of soil is appropriate. If there is too much, remove some like this. If there is not enough, add more. Place the metal plate with ridges face down on the soil. Make sure that the ridges are perpendicular to the direction of loading. Loading will be applied in the direction of the large hook on the testing box. Place the top cap on top of this, as well as a small metal ball which holds up the vertical load jig. Finally, record the mass of the remaining soil in the container. This will give the mass of the soil being used in the test. Use the two handles to lift the testing box and place it in the larger shear box like this. Remove the screws holding the two halves of the testing box together. Note that the top half of the shear testing box is now free to move around. Mount the load cell between the shear testing box's hook and the brace at the end by adjusting this screw. Adjust the horizontal strain gauge so that it's resting against the outer shear box. Place the loading jig on top of the testing box and move the vertical strain gauge on top of this. The vertical gauge should sit on the extended bit of metal on top of the jig. Load the testing software and make sure all 3 gauges are connected. This software will record displacement in both directions and load. The motor at this end can be adjusted to change the rate of displacement. We will change it to 1.3 millimeters per minute. For our experiment, we will be running the shear test at 3 levels of vertical load: 4 kilograms, 8 kilograms, and 16 kilograms. Apply 4 kilograms to the bottom of the loading jig. Zero the instruments and start the test. The software should start recording. Once the horizontal load peaks and then drops off, stop the test and save the data to a file. Reset the mechanism for the next test by moving the shear boxes to their original positions. Increase the load to 8 kilograms and repeat the procedure for the next test, and repeat it once again for 16 kilograms. For each of your tests, the horizontal load should climb to a maximum and then taper downward. The maximum load will increase with increasing confining pressure. For vertical displacement, your tests should look something like this. Determine the maximum load at each level of confining pressure. Plot horizontal load on the y-axis against the 3 confining pressures. Find the line of best fit to these 3 points. The apparent angle of shear resistance is the angle of this line. The apparent cohesion of the soil is the y-intercept of this line. Calculate both. Now that we've found both shear strength parameters, this concludes the direct shear test lab.